Hi Science 10s, welcome to part 3 of 4.2. We are looking at thermodynamics, which is the study of heat, and to do that we will go through some definitions of things like heat and temperature and thermal energy, and then we will flip over to a little bit of chapter 10 that talks about heat capacity so that we can do a calculation about how much heat certain substances can absorb, and that depends on their heat capacity. So you will need a calculator for this topic. I wrote down the textbook questions that relate to this lesson. For thermodynamics, it's 158 to 160 if you have your book, and in chapter 10.2, 357 to 377. When we're done, I will be assigning these 5 questions in page 21 to review with heat capacity. Check out these video links if you'd like about the joule. Remember, that's the unit of energy we're using. Some of our calculations you'll see will be variables given in kilojoules, so we'll just have to keep all the units straight so that they go with each other when we do calculations. We'll explain that as it comes. Remember these two guys, Mayer and Joule? Well, what came from their work is the law of conservation of energy that you've heard of before, that energy can't be created or destroyed. However, we can change something like the food you eat into energy to move, or plug in anything electrical and you can turn it into light, maybe sound, maybe heat, like in a toaster. And so these are examples of how energy can be changed from one form to another. And the kinetic molecular theory, at a molecular level, we're looking at how when molecules are moving, the faster they're moving, the more higher temperature they are. So the energy of motion is called kinetic energy, and so that comes to the kinetic molecular theory, where the thermal energy or heat from one object can be transferred to another object. And so kinetic energy is the energy of motion. It doesn't have to be particles, it could be anything object, like this guy moving up the hill or moving down the hill. That's kinetic energy. The guy who's sitting at the top not moving has potential energy. So we'll be talking about those two types of energy coming up in another chapter as well. So kinetic molecular energy, those movement of molecules, is the same as thermal energy because they're warmer if they're moving more. They are cooler if those particles are moving less. And so what it does move is, we've heard this before, the molecules that are moving more are in the warmer objects, so they would be the ones that are transferring their energy to a nearby cooler object. So if you touch a cold piece of metal, the cold isn't actually coming into your hand, it's the heat from your hand that's moving into the cold metal. So a definition of temperature, always think average energy. Okay, so average energy of the molecules in that substance, if they are average energy lower, they will be a lower temperature. If the average energy, they're moving faster, they will be a higher temperature. And work is, we saw that earlier, force times distance, is when you give some force and move something a certain distance. It's when you transfer mechanical energy from one object to another. So we're using motion of your arm to move the box, or motion of your arm and legs to move the box some distance. So that portion was the section of chapter 4.2 that is in our topic today. And the second half is the bit that's in 10.2 in your textbook, page 375. And here we talk about specific heat capacity, and we talk about water is a reference a lot. And so what was determined by joules is that to take one to get a 1 gram of water and increase it by 1 degree Celsius, you would need 1 gram of water, 1 degree Celsius, you would need 4.16 joules of work done in order to do that. So I think the 1 gram of water part is missing here. Okay, and so it is found in here though. And so this is actually a calculated heat capacity, and we compare other things to water. And the unit for specific heat capacity is a little c, and the symbol, and the unit is joules per gram degree Celsius. The degree should be right here. And joules per gram degree Celsius is the unit for specific heat capacity. Now, if we go back to the periodic, or a part of your periodic table data sheet has this specific heat capacity chart in it. And so you'll see that water here is stated as 4.19 joules per gram degree Celsius, but it also tells you what a lot of other specific heat capacities are of other substances. So steam, because there's less molecules in steam than liquid water, those are all farther apart, they'll have less capacity to grab heat. Dry air has no water in it, hardly any water, so it won't be able to grab and hold on to heat. And these things like metals have a very low heat capacity. They are very good conductors, and so heat will move through them fast. So these just show you that there are different substances that have different heat capacities, and as we do our calculations, you may have to turn to that chart. So water has these strong hydrogen bonds between the water molecules. So this is H, H, and oxygen, H, H, and oxygen. So the hydrogen bonds is between one water, here's one water, and another water here. The bond between a nearby hydrogen of one water and the oxygen of another water make a strong hydrogen bond. So it's for this reason that water has a relatively high melting point, high boiling point, high cohesion, high adhesion, and also high specific heat capacity. It's because of the hydrogen bond. Now, when we compare here the heat capacity of dry and moist air, remember, because there's water inside the moist air, it's able to has a capacity to hold on to more heat as those water droplets can absorb it. So it just makes sense. Here's a few heat capacities showing again that like things that are metallic are not good for holding on to heat, and that liquid water can hold on to heat more, twice as well as something like the gas or solid version of water. And so there's your little chart. Okay, so it says that why do we like moist air if it will take more energy to heat the moist air in our home? Why do we want a certain humidity in our home? And it has to do with health. Dry air irritates lungs, irritates eyes, irritates skin. So it is preferable to be in, it's easier to breathe moisture air. So that was the answer to that. And that brings us to our calculation today, which is looking for the amount of joules of energy that something has if it is, you have a certain mass of that substance, knowing in the chart what its heat capacity is, and you know what temperature it change happened. Then you can tell how much energy it would take to do that. And so you guys can take a look at this link. When we do this, we have to make sure if we're working with joules that we're using grams for the mass, that we're using specific heat capacity in joules per gram degree Celsius, and that we're using temperature in degrees Celsius. And so those will all cancel out so that our answer will be left the heat energy in joules. when they look at delta T, all that is subtracting the temperatures to see what the temperature change is. So for this first example, they tell you that the furnace broke and it's 2 degrees, but you wonder how much heat it would take to get it to 20 degrees. So you can see here, I just figured it out here in the green, that if you take the 20 degrees and subtract the 2 degrees, it's an 18 degree change. So you know what the value is for that one. We're talking about dry air here. And so the dry air from your chart is, and you guys can go back to your chart and check that, it's 1.00 joules per gram degree Celsius. I can go back to the chart and show you that, but it's right here. And the mass is given in kilograms here, but remember that we need to keep everything in grams so that the heat capacity that's in joules per gram degree Celsius can be used in your formula. So instead of 170 kilograms, you'll have to multiply that by 1,000 to make 170,000 grams to use in this question. So the mass, 170,000 grams, times the 1 for heat capacity, times the 18 degrees that we calculated, and your answer is 3.1 times 10 to the 6th joules, or else if you want to change that to megajoules, you can, but that is your answer. Second example we'll do to wrap up this section is this one that actually comes out and tells you the joules of energy, the mass, and the temperature change. So what you're looking for is the heat capacity. So for this kind of a question, remember that if Q is equal to mc delta T, if you're looking for one of these, and you just manipulate your formula, either because you've put it in this triangle and know that if you're looking for C, it will just be Q. Remember, you just cover C up. If you're looking for it, it leaves you with Q over M times the temperature change. Or you can simply look at it this way, going, if I want to leave C on my side by itself, I have to divide this side by the temperature change, divide this side by the temperature change, those can scratch out, and divide this side by the mass. So you also divide the other side by the mass, and these can cancel out. So it ends up being the exact same formula, whichever way you'd like to calculate for C, whichever works for you, you can do that. But it all works out to this same thing, that you have to take your Q, which is 3254, divided by the mass of 30 times the temperature change, which we see was 25 minus 10, which equals to 15 degrees. So you put your 15 degrees and your times by 30 at the bottom here. 30 times 15 degrees. At the top was your 3254. And when you divide that all up, your answer is going to be the heat capacity you were looking for, which is 7.23 joules per gram degree Celsius. Alrighty, so that's the end of this part 3 lesson, and your assignment as posted will be 5 questions starting on page 21, and you can check out the key after you do those questions, and